right, good evening, everyone. Welcome to another session of the makeup class. In tonight's lesson for DCIT 207, I'll be walking you through chapter 10 of the Stallings Manual. And this time I'll be using the Stallings Manual directly. We'll be discussing number bases. The recent session that we had with our lecturer hinted that in our exams, we are going to be dealing with a lot of questions concerning number bases. So at least that's what it sounded like. Give a thumbs up if you can hear me speak clearly. All right, so it looks like Mr. Joshua can hear me, but for some reason the others, okay, perhaps you can, maybe you are just not able to give a reaction. All right, thank you, Mr. Freeman. Okay, so for an advantage with this is that number systems are a concept that we have been familiar with ever since we were in primary or whatnot. And for that reason, it shouldn't be anything difficult to tackle. And also, due to the fact that we are allowed to use calculators, most of the conversions the calculator can handle. So I think it's best to teach the ones that you will use the calculator for, since it's going to be objective based. We just teach that once, and I believe a lot of you are familiar with that. I am not with a calculator right now, but I can show you some images to guide, and for the rest of it, that's on you. If you have a calculator, you take it and follow. That's what I meant when I said that's on you. So give me a sec. Okay, so take your calculators if you have them. Those who are not already familiar with this, it will just be about a 5 or 6 minute thing, and I'll walk you through it. For the rest of the session, we'll be solving questions concerning number systems that were inside the Stallings manual that requires some attention. So yeah. So if you want to do conversions using a calculator, okay, hold on. If you want to do conversions using a calculator, those who are already familiar with it, you first go to the mode on this side. So you can take a calculator and follow through with us. You come to mode right here and you click on that. So once you click on mode, the menu displays. And then when you are in there, you will just come to the option 4 of the menu where it says base N right here. And you select that. So selecting that will lead you to another page or another screen on your calculator. Let me see if I have a shot of that screen. Okay, I don't have a shot of that. Okay, yes. It will bring you to a screen like this one. So depending on the base that you have chosen, mostly it will be in a default base. In this case, it's in decimal. So what you're going to do is you can enter a number in decimal right now. For example, you can enter 451 or something. And after doing that, you hit equal to, and then you come down here to this row of keys here. You see, it has a display that shows some of the number systems. You see DEC on top of this key, X squared for decimal, HEX on top of this one for hex, BIN for binary, OCT for octal, and it even displays some of the hexadecimal digits, hexadecimal alphabets on this side. So if you enter a number like 451 and you hit equal to in decimal, it's going to be held in decimal. However, if you wish to convert it into another base, for example, hex, all you have to do is now come to this particular side here and tap hex, and then it's going to convert that value into the hexadecimal equivalent. So that's basically it. Okay, so you take your calculator, you punch. I think this is not the best way to show it. If you have calculators and you are following, then that's cool. If you have seen these before too, better still, let me show you a YouTube video on it, just for the conversion side. And once you've got those sides down, I think the remaining ones we can just discuss and then we are good to go. Okay. Okay, so here are some videos to watch, and then if you are following with your calculator, you can ask questions. Okay, so in the video, as you can see, he goes to mode, selects option 4 for the base. After doing that, he selects a particular base. So you choose whether you want the number you're about to enter. Maybe it's a hex number, so you select hex first by clicking this, by tapping this. Or perhaps it's a binary number, you tap binary or etc. etc. And after doing that, you enter the number itself. So after you tap here, it changes into that system. You enter the number. So in this case, he entered 1000. We know that's the binary equivalent of 8. So then he comes to the decimal. After doing this, he hits equal to, and he comes to this system again. He chooses decimal, and then it converts straight to the decimal number system. So that's basically how you do the conversions concerning that. The ones that you may not be able to do with a calculator are the ones that have to do with sign and magnitude representation, radix complementing, and then diminishing radix complementing, and that's all. But every other thing should be fine. Even if you have to deal with addition or subtraction in number basis, all you have to do is convert the number, since it's objectives, convert them into the decimal system, add or subtract, and when you're done, convert them back into the original number system. Answer on the, what do we call it? In the objective list or the alternative list. All right, so let's not waste my time. Let's get right into it and start working out some of the problems we see here. So I'll be using whatever ways I know, the ones that have made it convenient for me when I am dealing with number systems to tutor in this particular session, so that, if it is good for you, then you also stick to it as well, I guess. The first question on this sheet says that we are to count from 1 to 20 base 10. And it means we are in the decimal number system and we are supposed to count from 1 to 20 in the octal number system, in base 6, in base 5, and in base 3. So we are most familiar with every other base but mostly we don't talk about 6, 5, 8, 3. We talk about the typical bases that happen to be powers of 2. And then decimal number system, of course, because that one it is a familiar one that we normally use. If we were to count from 1 to 20, are you going to take your time to do the conversion for every single one all the way to the last? That will be a waste of time, seeing as you are dealing with objectives and then, there's a lot to handle and all that. So here's a little trick you can use in such a case. When you're counting in a particular base, for example, if we are counting in base 8, starting from 1, every number 1, 2, 3, 4, 5, 6, 7 fits perfectly inside the base 8. However, there are problems when it comes to numbers like 8 itself and 9, since they are larger than the sample space that we deal with when we are here. For that reason, whenever you get there, new digits must be used. So let's see how it will be when we are counting from 1 to 10, 8 to 20 in base 8. So we first have 1, that's normal. We have 2, that works. I'm sorry. So we have 2, that works. We have 3, that works. We have 4, that works. We have 5, 6, 7, and then 8 is what the first problem is. So the trick that I will use for this is when you are supposed to convert, what you have to do is find out how many times the base or the radix goes into the number. You write your remainder first, and then you write the quotient first and then the remainder second. Like in this case, 8 goes into 8 once, remainder 0. So then the next number is going to be 1, 0. So now study the pattern here. This becomes 1, 0. So from 7, we go to 1, 0 for the next value, next digit here. The one that will follow in this case is 9. 8 goes there once, remainder 1. The one that follows is 10. 8 goes there once, remainder 2. One that follows is 11. 8 goes there 1, remainder 3. One that goes is 12. 8 goes there 1, remainder 4. 13, 1, remainder 5. 14, 1, remainder 6. 15, 1, remainder 7. 16, 1, remainder 8. 17, 1, remainder 9. And 20. So now look here, there's a problem, sorry. So we have 1 remainder 6, 1 remainder 7, but then there cannot be a 1 remainder 8. There can't be an 8 because we are dealing with the octal number system. So everything gets must be between 0 and then all the way to what we call it, 8. That's here. So from 17, we cannot go to 18. So we have to check. And then we are trying to recognize patterns, okay? And then we are going to use that pattern recognition to apply to every...
Hello.
Sorry.
Yes, yeah. Sorry for interrupting. Yeah. Please. So if I'm getting you right, you said when we get to 7, then 8, we find the quotient and the other way. I don't remember.
Yes, so 8, we are trying to recognize the pattern. Yeah.
So 8 will go into 8, 1. Remember 0.
2 times. Yeah, it goes.
So I'm like, so when we get to 16, which is 15 in base 8, 16, 8 will go into 16 2 times, remainder 0. Shouldn't we have 2 remainder 0? I mean 20 there, 2 0 to be for 16.
Yes, please. Yeah, so we are getting there. So we are here, sorry. Yeah, I was trying to use the pattern recognition to draw out a few things. So that's sorry. So I want us to establish a pattern recognition system, and then we are going to apply that to every number. It's okay. So thank you, Mr. Price. So now from 17, you realize the problem that if we go with 18 at this point, as we mentioned earlier, 8 is outside the numbers of digits that we have inside the octal number system. So this prompts you to make a change somewhere. And then since you are dealing with the octal number system, you can actually change the first digits of the number. You can increase that from 1 to 2. And this allows you to use a new combination of digits. And this is possible because the octal number system allows you to use 2, unlike the binary where you can only use 0 and 1s. Same applies to binary. If I started with 0, 0, 1, 0, 1, 1, eventually what used to be a 1 will now become 1, 0. So for example, in binary, I can start with a 0, I can go to a 1. Or in other words, the same as 0, 1. Then the next value on this hand is going to be 2. Like so. So then you are allowed to convert this to that. But that's as far as you can convert them. The third one will also be 1, 1. And then the one that follows, you will still have to stick to these ones and then the zeros. But in the octal number system, on the other hand, we are allowed to change from 1 to 2. This means if I keep going, so let's keep going. We have 22, 23, 24. They are not 22, 23, 24 though, but they are representing numbers in octal. So we have 17. So now we have 18. So 2, 2, 2, 3, 2, 4. 19, this 20. If we wanted to go to 21, this will be our 21. That's in octal. This will be our 22. That's in octal. This will be our 23. That's in octal. But then once we get to this side, we run into another problem because we cannot have 28, can we? So then what happens? The base number changes from 2 this time to 3. And it follows in the sense that if we take the number, so we are at what? 22, 23. So 17, 18, 19, 20, 21, 22, 23. This is 24 right here. So this is going to be 30. It follows that if we are standing at the number 24, 8 goes here exactly 3 times and it leaves no remainder. So it follows there with 0. So the only places you will have to be looking out for, or where you will actually have to be applying your divisions of 8, is exactly when you are transitioning from a digit that's is at the peak of the number system you are dealing with. In this case, whenever we reach 7, if you are moving to a number that has 8 in it, this is when you should consider dividing by 8 and then applying the remainder idea. This way, you'll be faster in generating the system. So in this case, the only places where we actually had to do such conversions were at this point, and then at this point. You realize after we had divided and we got 1, 0 here, we could just go ahead and count 1, 1, 1, 2, 1, 3, 1, 4, all the way to the end. It just makes you faster in when you're applying this, especially since we'll be dealing with objectives. You won't have to show much working. All you will have to show is your answer. So coming up with how to figure the answer out fast becomes an advantage to you. Let's apply the same idea, but this time to base 6. So now say I want to count from 1 to 20, but this time in base 6. So we do the same thing. There's 1, there's 2, there's 3, there's 4, there is 5, but there can't be a 6, can there? There can't be a 6, so we start again. So 1, 0. 6 goes into itself once, remember 0. So 7, this is 8, this is 9, and this is 10. This is 11, and then this is 12. So 6 goes into 12 two times, sorry, with a remainder of 0. So this is 12 like this. 6 goes into 12 two times with a remainder of 0. So the only, right there. The only reason why at this point we are actually using the division to check is the fact that we are transitioning from the peak, that's 5. If we move on to 6, it's impossible, and that's the only time you have to check. So from here on, we can say, so 21, 22, 23, we have 24, we have 25, and then we run into another problem. So we can't use 26. So then you have to consider doing divisions again. So we were at, this is 12, 13, 14, 15, this is 16, that's 17. So 18 is going to be 3, remainder 0, just like that. So remainder 0. It continues that way. The one that will follow will be 19, and then the one that follows is 20, all the way to the end. So basically, you just have to be doing the changes at where you realize the 6 is coming in because you're in the base 6. So do you get the idea that I'm trying to put across? So you realize that when we're using the octal number system, once we go to 16, it becomes 2, 0, 2, 1, 2, 2, 2, 3, 2, 4, 2, 5. Once we get to 2, 6, we divide again, and then we have 3, 0, 3, 1, 3, 2, 3, 3, all the way to when you get to 8. In the case of the base 5, same idea. So we count, let's apply the idea to base 5, and let's see if we can come up with the answer. So you help me do the counting, okay? I'm going to select one person at random and see if you can apply what we just did, if you understood this, that is. So if we are counting from 1 to 20 in base 5, yes, anti-divider. Divider, your hand
No,
went
no,
up.
no, no. No,
Okay.
it's okay.
All right. So please, to anyone here, okay, let me start with Mr. Prince. Mr. Prince, would you like to give it a try?
All right, sure.
Yeah. So let's count from 1 to 20 in the base 5 system. So we go. Yes.
So we have
1,
1 to 5, obviously. 1, 2, 3, 4, 5.
1, 2, 3, 4. So you can't have 5. That's the problem
Yes,
because 5 is
yes,
above.
yes, yes.
Okay,
Yes,
please.
sorry about that. Sorry.
Yeah,
So
yeah.
now we would have 1, 0,
And good. 1, 0,
then 1, 1,
1, 1,
1, 2,
1, 2,
1, 3,
1, 3,
1, 4,
1, 4.
then 2, 0,
Excellent. So 2, 0. Then 2,
two
1.
one,
Yes.
two
2,
two,
2. Yes.
2, 3,
2, 3. Yes.
2, 4.
2, 4. Then we have 3, 0.
Hello?
So we have 3, 0,
3-0.
right? Yes. So we have 15.
Yeah.
Yes.
Then 3, 1, 3,
Yes.
2, 3, 3, and 3, 4. And then we have 4, 0. So now we are 20.
4-0.
Yes. So we are 20. Okay, so then that's how you apply it practically, and it makes you very fast. So let's say you have been given objectives or something, and they're telling you to determine which of these is a count in the is a correct count in base 5 or 1 to 20 in base 10. You just have to analyze using what you already know. You know where the conversion is necessary. You are good to go. Let's apply the same idea, but this time let's use it in base 3 and see. So who would like to attempt that one, base 3? Yes, anti-divider, let's go.
Yeah. So 1 to
1, 2,
1-0.
1, 0,
1-1.
1, 1,
1-2.
1, 2, 2, 0,
2-0. Yeah.
2, 0, 2,
2-1.
1, mhm,
2-2.
2, 2,
3-0.
3, and 0. So we have 9, yes?
Yeah. 3-3.
3,
3-1.
1, mhm, 3,
3-2.
2, and then 4, 0.
4-0.
Yes. So 4, 1,
4-1.
yes. 4,
4-2.
2, and 5, 0.
5-0.
So we have 15, 5,
Yeah. So
1,
5-1.
5, 2,
5-2.
6, 0. We have
6-0.
18, and then we have
6-1.
6, 1, 6, 2. We have
2.
20.
Yeah.
Yeah, so we are at 20. Very good, very good. So that's pretty much it. So please, this is how you do counting, then provided you are doing from base 10 into another number base. Okay, that's all there is to it. Okay. So it's safe to say that if the number was given in base 8 and I'm supposed to count in base 3, all you have to do is change it first to base 10 and then count from base 10 to base 3. So for example, if I have been given a few numbers, maybe from 1 to 5 in a particular base, perhaps in base 5, and then I've
Please, can you
counted
take
in,
that out again?
okay, I was saying that if a count has been done in base 3, and you are supposed, or maybe a count has been done in base 5, better still, and you're supposed to count that same thing in base 3. The best way to do it is first convert it, or in your mind, think of it as your base 10, and then change that base 10 directly into base 3. So for example, if I tell you that this is a count from 1 to 10 in base 5, that would be 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 10. And I tell you to make the same count, but this time in base 3. all you will have to do is picture this as being inside the decimal number system, because if you change to the decimal, it's easier to convert into every other form. And in the decimal number system, do the same counts by overlooking all these numbers. Just go ahead and do your 1 for base 3, your 2 for base 3, your 3 for base 3, your 4, your 5, your 6, and in that order all the way till you get to 10. So you can just go ahead and overlook the digits at the top and then just think about it being in base 10, and then you apply that to convert. Now, what if the thing was already given in that number system? So for example, you've been given a particular digit in one number system, maybe in base 5. I tell you that there is a number such as 80, and I tell you to write its what do we call it, base 3 form. Write 80, which is in base 5, as a base 3 number. Same idea, convert it into its base 10 equivalent and convert that base 10 into a base 3. So what do I mean by that? You know, if you want to convert every number in base 10, it follows a fixed pattern. You just have to multiply the number by its weights, and then basically you will have the answer. For example, this 80 right here, if I am supposed to convert it into base 10, we just give every single digit in this number a power. And we know that this is 8 to the power 0 to the power 0, and then this is 8 to the power 1. So you can overlook the 0 to the power 0 because it will make no difference. It will still be a 0. 8 to the power 1, on the other hand, in the base 5 is the same as 8 times 5.
Times 5.
Yes, to the power 1, which is the same as 8 times 5. And that basically gives us 40. We know this already, yes. And then for this one, I won't bother to take it into detail because you have your calculators to help you with those conversions. However, if you are confused, you can just say so and I'll explain that. And if we know the equivalent of it here is 40, we just have to convert that into the base 3 number system. And we know that to do that, you can just punch on your calculator, even though it doesn't mention base 3 explicitly. But another way to do it is keep dividing by 3, keep the remainders till you come to your last digit, which will be a 0. And then we know that already, but let's work it anyway. So for example, if I wanted to convert my 40 into a base 3 number, I'll just, the division table approach is the fastest way to go every time. So we are dealing with 40. We are dividing by 3. We keep the remainders on this side, and then we put the quotients down here. So 3, the closest 3 can get to 40 is what? 3 times 13. That gives us 39. So there's a remainder of 1, right? And we can still continue the division since we've not reached the 0 as a quotient. So 3 can go here. The closest 3 can go here is 12. So 3, 4, 12. That's as close as we get. And then there's a remainder of 1. 3 can also divide our 4. 3 goes here, 1. 3, 1, 3. So there's a remainder of 1. 3 doesn't divide 1 though. So 3 doesn't divide 1. However, there will still be a remainder of 1 that we couldn't divide. So in order to get the final number, we just write this number bottom up. So our answer is 1, 1,
3
1,
goes
1.
into 3, 1 without a remainder.
Come again. Oh,
3 goes
sorry.
into 3,
That's
1
right.
without a remainder.
That's at this spot, right? No, you see, 3 goes into 3 ones without a remainder. However, we are dealing with 4. You understand? It goes into 3 ones. 3 is the greatest multiple of 3 that is still less than 4 that 3 can divide. But after that division, there is still a remainder of 1 to reach 4. That remainder is what we have put on this side. Please, who was the speaker? I'm addressing that.
It was me, but then I'm a bit confused.
Oh, okay. So sorry. Then let me just take it slow. Okay. So I'm just moving this fast because I assume we all know this. I know you do. Maybe it's just a little forgetfulness, but if you really need some clarification, just say so. Okay. So we are trying to simplify, change 40, which used to be 80 in base 5, into its base 3 equivalent. And I said in order to do that, you first have to pass through base 10. It's simpler to do it that way. So passing through base 10 will mean that you multiply each of the digits here by their respective weights to find their values, and then you add them together when you do that. Normally, it will be 8 times 5 raised to the power 1 plus the second digit, which is 0 times 5 raised to the power 0. But since we know that the product of 0 with any number is still 0, we have discarded all of that just so we don't waste our time. And we are just focusing on 8 times 5 to the power 1. That's just 8 times 5, and that gives us 40. So now that we have the decimal equivalents, we can now use the general rule for converting from decimal to any other base to do the conversion. What we have to do is we divide repeatedly by the radix. In this case, base 3, so the radix is 3. We divide repeatedly, we keep the remainders, and we keep dividing till we get to a 0. So we start by dividing 40 into 3 parts. If I divide 40 by 3, I get 13. So 3 times 3 goes here 13 times. That's the idea. And then the answer to that division is 39. 3 times 13 is 39. So you see there is a remainder of 1 that will give us the 40. So that remainder is written here. Okay. We follow up with the second division. We are trying to reduce this number till we come to a 0. So 3 divides 13 as well. However, it can only go there when we are using 12. 12 is the closest multiple of 3 to 13. So we use that. So 3 goes into 12 4 times. Remember, the quotient is what you want. You don't want that multiplier or that product. You just want the quotient. So 3 4 12. And you see, we are 1 less than 13 still. We are still not at 13. So that remainder is retained here. And then we still follow up with a division by 3 again. So over here, the closest we can get to 4 is 313. So 3 can only go into 4 once. And then it gives us a product of 3. However, that factor is not equal to the 4 we are looking for. You see that we are still 1 less than 4, so it means there is a remainder. So that remainder 1, it must be stated, it goes here, like this. We are still not done. We only stop when the quotient is finally a 0. So maybe the last step will do us justice. 3 doesn't divide 1, so it goes there 0 times. However, 3 times 0 is 0. And as you can see, 0 is still 1 less than 1. So then there is a final remainder of 1. So Mr. Prince, that is where that remainder 1 came from. We couldn't actually divide fully into any number. Yes, sir. So finally, to write your answer, you just write from the bottom up to the top, always. The reason being that this will always be the most significant number, and this will be the least significant number. So when you're arranging them, in this case, it's just a bunch of ones, so it will not make any difference. 1, 1, 1, 1. So even if you wrote it down, in this case, it will be correct. But that doesn't necessarily mean that will be the case all the time. So this is the most significant number, and then it rises towards the top. So this is 1111 base 3. And it's important to indicate the base. As you can see, 1111 may also be a binary number. It may as well be in any other base there is. Is that clear? Yeah. So if you are given any digits or any number in a particular base, you have to convert it into another base. First go through base 10, and then from base 10, you go to that base. All right. So I'm going to give you one. Let's just tackle it quickly. I'll try to give you one that your calculator can tackle, so that someone will not just punch it on the calculator for us. You have the
Okay.
someone has their mic unmuted, so please mute. Okay. Okay. So let's use the number. Let's see which number can we use. So 45, 45. I don't know if I'm right to call it 45 because it's not in the decimal system. Base 6. Let's change 45 base 6 into let's see, a binary number. Okay, that will be okay. There are several ways you can do that. So you just go ahead. Yeah, calculator can do that one. Sorry, not into a binary. Change it into a base 5 number. Good. So change 45 base 6 into a base 5 number. Remember to first go through decimal. It's easier that way.
Yeah, hello. Please, are we going
Yeah.
to change the 45 into bine?
No, base 5. We are changing it into a base 5 number. So it's best to pass through base 10 and then from base 10 to base 5. So find the base 10 equivalent of 45 and then convert that to a base 5. So I'll put some time on it so that we can move fast. It's now 8, 9. When it's 8:11, that's in 2 minutes. I'll stop you there. Okay, 2 minutes up. Are we ready or should we go together? Oh, you're almost there. Mr. Joshua, Mr. Freeman, Mr. Prince, Santi Vida. How many people are on this?
I'm done.
Are done. All right, all right. So please share with us. First of all, what was your answer in decimal first? Or you went through a different channel?
My answer in decimal was 29 base 10.
Okay, 29 is 10. All right, that's cool. And then you converted that to base 5, and your answer was
104 base 5.
104 is 5. Okay. So since Mr. Freeman has an answer, let's wait on one more person. Let's see
The same
if you
answer.
the same answer. Okay, so I would like to believe that that's correct. So let's.
The same answer here.
All right, that's good. So what I believe you did on this side was 4 times 10 raised to the power 1, which is still the same as 4 times 10, plus 5 times 10 raised to the power 0, which is just the same as 5. So 4 times 10 is 40. Sorry, we are doing in base 6. So 4 times 6 raised to the power 1, which is still the same as 4 times 6. And then 5 times 6 raised to the power 0, which is still the same as 5. So that's 24 plus 5, that gives us 29 base 10. So first one is correct. And then we convert 29 base 10 into base 5 by repeatedly dividing it. So let's see that. So 5 here, we have our 29. Then our remainder goes here. 5 goes into 29 5 times. Then it gives us a remainder of 4. And then 5 goes into 5 once, gives us a remainder of 0. 5 is unable to divide 1, so there's no quotient, but it gives us a remainder of 1. So from the bottom up, we have 104 and base 5. So yes, thank you, Mr. Freeman, excellence, and everyone else. The answers were right. Okay, so we move on. Other than numbers 1.1 base 2, 1.4 base 10, 1.5 base 16 from smallest to largest. When you see questions like this, I want you to think back to forms of fractions. You see, there are several forms you can write a fraction in. You can write it as a percentage, a decimal, whatever. But in order to compare these respective forms, you have to find, or you have to choose a common form that you can put all the fractions in, and then you can easily compare and order them. Same idea applies to when you are dealing with fractions that have different denominators even. You have to change them into fractions that have the same denominator. That way you can easily compare the numerators, or even when you're adding or subtracting fractions. That very same idea is what you apply to doing questions like this on the number systems. So it means when you're adding different number systems, or you are subtracting, or you're ordering, or you are comparing, you have to make sure that they are all in the same number system. And we can all agree that changing from every number system to base 10 or to the binary number system is almost always simple. So why not change all the numbers given to us into base 10 first? And that way we can easily compare our new values. Okay, so we have 1.1, we have 1.4, and then we have 1.5. You notice that 1.4 is already in base 10, so it means we don't need to change that. But let's change 1.1 into base 10. So 1.1. In base 10, we just take 1 times the radix, right? In this case, is 2. Let's assign them places, by the way. So this is to the right of the decimal point, you have -1, and then the digit that follows is to the first place of ones, like this. Do we all agree to that? Okay,
Please
I
come
assume you
again.
do. Okay. What I'm saying is, if we take the number 1.1, to the right of the decimal place, to this side, we already know what the places are. We have ones, so to the power 0, we have tens, that's to the power 1, and then we have hundreds to the power 2, etc., etc. But on to the right side, though, we do not have those places, but rather we have division places. So to find the value of a digit in decimal, we know that we divide by the radix. So in this case, it is not going to be to the power a positive power, but rather to a negative power. That's an inverse power indicating division. So then from 0 this time, we go -1. If there was another one here, it would have been to the power -2, and then to the power -3, and it continues in that order. So I mean, the further away you move from the point, the smaller your value gets. That's the idea. Is that clear?
Yes, please.
Good. So now that we have done the power assignments, we can just convert the number places. So this will be 1 times the radix, which is 2 to the power 0. And then we know 2 to the power 0 is the same as 1. So that's basically 1 times 1, right? And then this guy, on the other hand, is 1 times 2 raised to the power -1. And then which is the same as 1 times 1 divided by 2. So 1 times 2 raised to the power -1 is the same as 1 divided by 2. So 1 times 2 to the power 0 is 1. And then 1 divided by 2 is what? 0.5. So 1 plus 0.5 gives us 1.5. So it means the base 10 equivalent of 1.1 is 1.5, like this. So in base 10. So that's it for that first number. Any questions so far? All right, none. So the next thing to do is this already in base 10, so we don't need to worry about that. We have to change 1.5 to its base 10 equivalent. You see it's in base 16. So we apply the same idea here, but this time the radix we are multiplying by 16. So we assign our places. This is to the power -1, whereas this is to the power 0. So the first digit is going to be 1 times 16 raised to the power 0, which is the same as 1 times 1, because 16 raised to the power 0 is 1. And then the second digit, on the other hand, is going to be 5 times 16 raised to the power -1, which is the same as 5 divided by 16, like so. So we have 1 plus 5 divided by 16. So please, if you have calculators, punch that for me, or better still, I can be working that out here. But if you have a calculator, please punch that for me. So 16, and then we have 5 here. So we bring your points, add a 0. 16 times 3, that's 48. Subtract, left with 2. 16 doesn't divide 2, there's a point, you add a 0. 16 goes here 1. 16, there's a remainder of 4. 16 doesn't divide 4, there's a point, you add a 0. 16 times 2, that's 32. So it keeps going. Or I'd like to believe it stops around here. So 40 minus 32 gives us 8, yes. And the point at the 0, and 16 times 5 is 18. Okay, so it stops here. So 0.3125, that will be the equivalent of the 5 over 16 there. So we have 1 plus 0.3125. And then it brings us to 1.3125. And that's also in base 10. So it means this is the base 10 equivalent of the 1.5 base 16 right here. So now that we know all three, we can now arrange them in the desired thing. And remember, since you are working objectives in a question like this, when base 2, base 10, base 16 can all be punched on a calculator, it's safer to punch on a calculator before you do the ordering. Yes, Mr. Freeman.
Yes, please. I had 0.375. That's for the decimal part.
The decimal part of
The
the 5 over
question.
16.
I had 0.375. So in all, I got
That's
1.375.
Please, that's for the 5 divided by 16.
Yes, please.
All right. Okay.
Oh, okay.
So,
Hold on. I
yeah.
think I didn't do it well. Hold on.
Okay. So please check 5 divided by
Oh, okay,
16
yeah,
and
it's
see.
true. It's true. I did it 1.6 rather. Sorry.
Okay. Oh, no worries. No
It's
worries.
correct.
All right.
Thank you.
All right, Charlie. Thanks. Okay, so then the numbers are 1.12, which is now 1.5 base 10. So it's faster to use a calculator for this. So then from what we saw earlier, you can just take your calculator, you go to mode, you first select the number base. In this case, you select binary. So binary is one of the keys on the keyboard or on your calculator has been. So after you select option 4 in mode, you select that bin. And once you tap that, it waits for you to enter a binary number. So you enter 1.1, you hit equal to, and after hitting that, look for the key that has des or DEC on top. You hit that, it will convert the 1.1 base 2 into 1.5 base 10. So now you will have your base 10 equivalent. You do the same thing for this guy. This time, after you go to mode, you select 16 to take an input in base
But
16.
please, you are talking
Yeah,
fast. I can't hear you well.
I'm sorry, yo. We explained from the
Journalist.
start of No, don't worry, don't worry. And when we were working, we started at the start of the lesson. I showed a video and then a way to do conversion using calculators.
Yes, I
So
know.
it's
I know how to use that one.
so that's what I'm reiterating there. And I'm I'm just saying it fast because I assume you know it already. But I'm sorry, okay, I do get carried away sometimes and I speak fast. So what I was saying is, let me display that very screen again. One way you can do that is on your calculator. You can go to mode. That's over here, this side. And then after you hit mode, it will take you to this page right here. And at this page, you see at option 4, it says base N. It means you are doing a base conversion. So you select 4 and it takes you to that. When you go there, after you select that, it takes you to a page that waits for you to select a base in which you'll be entering your inputs. So for example, if you're entering an input in base 2, you see on top of the log key, it says BIN, that's for binary. So if your input is going to be in binary, just press that key and then this is automatically going to change into that number system. Then you can enter a binary number. So if we are changing the first number 1.1 in binary, we will just come to this side after we did mode and went to option 4. We'll come to log, we hit that, and then it's wait for a binary input. So then we enter 1.1. After entering the 1.1, you hit equal to, and then it saves that number as a binary number. The next thing you want to do is the base you are trying to convert it into. In this case, you are converting it to decimal. You will just come back to the same keyboard, and then you see this X square key that has DEC for decimal. You tap that, and then after tapping that, it's going to change the 1.1 that was in binary into its decimal equivalent, and that's that. So then you will just write that down and then you now go to the base 16 number. So that base 16 number was what? Was a 1.5. So you change the 1.5 also into a base 16 number. All you have to do is you hit mode this time you select hex here. That means you're taking a hex input. So mode option 4 hex. You give it the 1.5 equal to, it saves it in hex. And finally, you come back and click or tap press decimal to convert that hex value and give you a decimal output. Is that clear? Yes,
Yes,
Mr.
please.
Freeman. Yeah, Mr. Freeman.
I just sent you some setup view right now on WhatsApp. I don't know if you just take a quick look at it whilst you are teaching. It will
Oh,
help.
okay. All right. I believe it's is it a calculator interface for Casio?
Yes, please.
Okay, let me look at it. If it will not take long to set up, I think we can just use that course.
No,
Oh,
it
okay.
won't take long.
If it won't take long by my machine, now I bought down rough, so all right, thank you, Charlie. Yeah. So you don't worry, when the machine is ready, it will open the file. So yeah, thank you, boss Freeman. All right. So with that out of the way, now we have our new decimal equivalents of the values that we were given. But remember, that was not the end point of the question. The question was asking us to order them. So we now have to arrange them in an order. Did it say ascending or descending order of magnitude? I'm coming. This guy is in the way. So it says from smallest to largest, so in ascending order. So let's just arrange them from smallest to largest. So obviously the smallest number here is 1.3. You know, in decimal numbers, when you are comparing the digits that are farther away from the zero, they're actually smaller than, from the points are smaller than you think. So don't say this one has more digits, so it's larger, right? I believe we know that. So just compare the digits in their respective places. For example, 1.4, the next number is 1.5, and then the next number is 1.3125. So if you compare the places, so we have these are the digits in ones, and they are all a one. So we cannot really do a comparison there. But if we come to the digits in hundreds, in the tens, that's this side, TENCH, the decimal place. This is 4, that's 5, and this is 3. Obviously, this is automatically the smallest number. Therefore, the smallest number in the chain is going to be the value that corresponds to 1.3125, which is 1.5. And remember, in your objective, mostly to make the examiner's job easier, the questions are mostly set, but the answers will still be in the original forms they came in. The reason is simple. You see, you may choose to convert them into hex numbers and then order them. I may choose binary, someone may choose decimal. So the best way the lecturer or the examiner can work around that is to I'll provide the answers in the same form that the questions were given. And that way you will just have to match your new order with that. So as I said, this is the smallest number. So I expect to see in my answer that this guy comes first. So this will be number 1. And then 1.5, 1.4 is the second smallest number. So it means this guy should come second. And finally, this should come third. So smallest and then largest. Yeah. So yeah, that's that. We are taking quite a while on this. Let me see. So let's proceed. Next one says we have to perform the indicated base conversions. So it's basically the same as what we did earlier. And so we are going to just do one example, just one. And then when we are done with that, we can, proceed. So this one says we have to convert 12212 base 3 to base 9. There's actually a relationship that numbers like this share. And okay, I think that reflects directly on question 10. So we'll use that. But before we move on to question 10.4, before we move on to that, I want us to just tackle this. And when we look at the relationship, we are going to use that idea to work out this example right here. So please tackle this. We are converting 3124 base 312 base 4 to base 7. So the same thing we looked at earlier. First change it into a base 10, and then from base 10 to base 7. So please, how about it?
Hello.
Yeah.
Oh, okay. My network dropped, so I'm kind of lost. What's going on?
Okay, so there's a question here that says we have to convert 312 base 4 to base 7. But since it's a direct reflection of what we were looking at the top here, I was saying we should tackle that and then give our answers when we are done.
Oh, okay. That's nice. Thanks.
Yeah. Okay, that's quite some time. Please, has anyone worked it out? Antivida, Mr. Freeman, Mr. Richard, Mr. Joshua, if he's still here, anyone, Mr. Prince. If you have, please share what you have with
Still
us.
working around it.
Yeah, working
All
around
right.
it. Okay.
So
All right, Mr.
so
Freeman.
from 312 base 4. I first changed it to base 10 as required.
Okay.
And I got 54 base 10.
Okay.
Then I changed
54.
that to
All right.
base 7. That would be 105 base 7.
105. Okay. So it says this is base 10 and this is base 7. So I just want one more person to say I got the same answer and then we proceed. Or maybe we have different answers too.
Yes, so I'm also getting 105 base 7.
Okay. So I believe the answer is correct. And antivida, I would like to believe you're also very close to the answer. So I think we are on track. So to those who joined us not too long ago, if you do not know what is happening, we just changed 312 base 4 to its base 10 equivalent. So we changed that base 10 back to base 7. It's faster to work it that way. So if I change 312 to base 10, it's just going to be 3, since it's in base 4, so times 4 raised to the power 2. That's the weight of 3. The idea is this is 2 raised to the power 0, 1 raised to the power 1, and then 3 raised to the power 2. We know how that works already. So this is 3 times 2 raised to the power 4. And the next one will be 1 times 4 raised to the power 0. 1 times 4 raised to the power 1, which is the same as 1 times 4, which is still 4. And then the last one is going to be 2 times 4 raised to the power 0, which is the same as 2 times 1, which is still 2. So 4 is 16, and then 3 times 16 is 48, and 4 plus 2 is 6. So 6 plus 48 gives us 54. So first one is correct. Excellent. And then for the next, if we want to change it, we just have to repeatedly
Yes, I
divide.
got the same answer.
Excellent. That's good. Excellent. So we have to repeatedly divide 54 by 7 and keep taking our reminders. So if I do 54 divided by 7, what can I get first? 7, 7, 49 is as close as we get, right? Am I right? 7, 7, 49. So that will be 7 here. And then we'll be having a remainder of 5, like this. And then the next one, 7 goes here, 1, with a remainder of 0. And finally, 7 goes here, 0, with a remainder of 1. So writing from the bottom up, we have 105, and then it's in base 7. So yes, correct. So you will see this answer displayed boldly in your objectives. Now, let's look at question 10. And we are going to use the idea we get from question 10 to do question D very simply than it's supposed to be. What generalizations can you draw about converting, and you can know this, a number from one base to a power of that base? For example, when you're converting from base 3 to base 9, which is the same as base 3 squared, or base 2 to base 4, which is the same as base 2 squared, or base 8 to, or from base 2 to base 8, which is the same as base 2 to the power 3. And the easiest way to explain this to you is looking at binary conversions into other numbers that are considered as powers of 2. For example, if I want to convert from binary to octal, since we know that octal is equivalent to binary to the power 3, any octal number, its binary form is basically the binary number but in groups of 3. So for example, if I wanted to convert the binary number 1, 1, 0, 1, 1, 0, 1 into its octal equivalent, all I have to do is pair up these numbers in groups of 3 like so. And then if the last number does not have enough digits to be counted as a group of 3, you can just add more digits to it. So you always start from the least significant side, working towards the most significant here. And then you can convert each of these ones here into their octal equivalent. And then once you do that, you're good to go. So I can convert all these ones into their decimal equivalents and change that decimal part into the octal part. It will give me a perfect answer. That's what I would get. And that would be the same as what I would get if I just converted everything as one big number into decimal and converted that back to octal. So this is because we are grouping in groups of 3 because we know that for every single value here, right? It's equivalent to 2 to the power 3 for every single binary number. So if I take one single binary number, I have to raise it to the power 3 before I get its octal equivalent. So we group in groups of 3 like this to represent that relationship. The same idea applies to hex. If I want to change from binary to hexal, that's 16. You know that 16 is 2 to the power 4. So what do we do here? All we have to do is this time we group those 16 bits. When we are converting to binary, you group them in groups of 4. So when you're converting from binary, into hex, you just do the grouping in groups of 4. This idea tells us something, that for any number system where our where our base b is just basically to the power n of a certain number, we just have to find n groups of that number when we are doing the conversion. So then that's basically the relationship. You have to find n groups of the number when you are doing the conversion in order to be able to convert right. That idea can be applied here. If I want to change a number in base 3 to base 9, all I have to do is take the base 3 number and then I form n groups of it. Then I convert each of the n groups, then I can get the base 9 equivalent. So I'll convert each of the n groups into base 10, and finally I'll convert that into base 9. What does this mean? If I take the number 1, 2, 2, 1, 2, 3 in base 3, and I want to change it to base 9, base 3 and base 9 share a relationship that base 3 squared is equivalent to base 9. This means the n groups I'll be forming in this case is how many digits will be in every group in this case, from what we just said. So I expect a contribution from your side. I said we form n groups of that number. The n is basically the power. So in this case, from base 3 to base 9, how many groups will we form according to that n group principle that I mentioned?
Please, I'm not getting what I didn't get what you said, but what I'm thinking right now is maybe if you get 4 groups.
Oh, okay. All right. All right. I'll come back to that. Mr. Freeman, your hand is up.
2 groups.
2 groups. Excellent. So for those who didn't answer, I assume you share wider sentiments. So I'm going to take my time to explain this again. And Mr. Freeman is right. It's actually 2 groups. Let's see what is happening. What I'm implying is this, that if we observe the relationship that the base 2 numbers, that's binary numbers, share with other bases that are powers of 2, you realize one thing. If we are converting from base 2 to base 8, if you are converting from base 8 to base 2 or base 2 to base 8, either way, you realize that since base 8 is basically base 2 to the power 3, the relationship they share is for every binary number, for example, 1, 0, 1, 1. If I want to be 1, 1, 1 or 1, 1, 1, yeah, like this. If I want to convert any binary number into its base 8 equivalent, since I know they share a relationship that says 2 to the power 3 is equivalent to this, I just have to break them into groups of 3. And each group of 3 represents a single octal value. Like each group of 3 here is equivalent to one single digit inside octal. That's due to the fact that we are saying 2 to the power 3. So every single 3-digit group in binary is an octal. That's the whole idea here. The same applies to base 16. So in the case of this guy, if I wanted to convert this to binary, I just have to change this to its if I want to change it to octal, sorry, I have to change this to its decimal equivalent. So 111 is 7 in decimal, and then 101 is what 5 in decimal, right? And after getting this, I can now change them into their octal equivalent too. And we know that in octal, these numbers, I think they will stay the same, right? 5, 7, and octal. Okay, you can change them into octal by dividing little by little and all that, yes. So they won't stay the same. We have done it in decimal. So then the whole idea is, since we know that 2 to the power 3 is a relationship that the binary shares with octal, we broke them into groups of 3. In the case of hex, if I wanted to convert from binary, but this time to hex, the relationship they share is 2 to the power 4. So if I were to form groups, this time I'll be breaking them into 4 groups each. So if I have a number like 1, 1, 0, 1, 0, 1, 1, 1, and I want to convert it into its hexadecimal equivalent, since the relationship they share is 2 to the power 4, that's binary and hex, I will just break them into 4 groups. Like that's what we already know. And I'm saying, if you observe this, there is a pattern. You realize that the number of groups, the number of digits in a group we break it into is equivalent to the power that stands here. In this case, power 3, we broke into groups of 3. And in this case, power 4, we are breaking into groups of 4. So therefore, we come to a conclusion that for any number system, if it shares a relationship with another number system such that b to the power n is that relationship, to convert from system B into the other number system, all you have to do is group them into groups of n. So if n is 5, you group into groups of 5. If the power is 7, you group them into groups of 7. If the power is 3, you group them into groups of 3, provided that's the relationship that the two number bases share. Okay, Antivider, that's what I was saying the first time. Is it clearer?
Please. Thank you. Yes, please.
Good.
Okay.
Now, with that in mind, yes, please. So with that in mind, I'm asking that if we are starting at this number system, that's base 3, and we want to convert it to base 9, the first question to ask yourself, so this right here is the answer to this question, okay? So your answer is going to be that for every number system, for number systems that share a relationship b to the power n, you form n groups of the base b in order to get the equivalent, or in order to find an equivalent for the other number system that is in question. Okay, so in objectives, I don't know how exactly the question will be phrased, but remember that the relationship they share, if it's b to the power n, you just find n groups. Okay, so no matter how the question will be phrased, it will be along, the answers will be along those lines, in case you see something like that. Now back to you. I'm saying with that in mind, if I have this number here and it's in base 3, how many groups am I to form to get its base 9 equivalent when I do the conversion in decimal? So the type of relationship that base 3 shares with base 9 is 3 squared. So it means b is 3 and then the n in this question is 2. So we just have to find 2 groups each. So I'm going to break the number 1, 2, 2, 2, 1, 2, 2, 1, 2 into 2, 2, 2 groups. So let's do that. I have 1, 2, 2, 1, 2. We break them in 2 groups each. So this is one group, this is another group, and then the last group is obviously too small, so we can increase it's a 0. That's the most significant bit, right? Like this. And we convert each of these groups into their decimal equivalents. So let's change them into their decimal equivalents and see what we have. Right. So we start with the first one. This is 1, 2. If we change it into our decimal equivalent, this is 2 to the power, this is 3 to the power 0, this is 3 to the power 1, like that. This will also be a 0, 1, and this will also be a 0, 1. The reason why this is convenient is we don't have to deal with heavy weights, just smaller weights. So each one is just to the power 1. If we're doing it straight, it would have been 0, 1, 2, 3, 4, 5. That makes it heavier when you're dealing with them. But over here, we just have to do 2 times 3 to the power 0, which is basically the same as 2 times 1, which is 2, plus 1 times 3 to the power 1, which is the same as 1 times 3, which is 3. So it means this number in decimal is going to be 5. We do the same thing for this guy right here. So 2 times 3 raised to the power 0, that's the same as 2 times 1, and that gives us 2. And then we have 2 times 3 raised to the power 1. That's the same as 2 times 3, which is 6. So 6 plus 2, that gives us 8, like this. On this side, we have 1 times 3 raised to the power 0, which is the same as 1 times 1, that gives us 1. This right here is the decimal equivalent, 185, like this. Then it also happens to be the exact base 9 equivalent too. It saves us the trouble of having to go to do the long division step and all that to get it. And this happens between numbers that share a relationship of b to the power n. So you can go ahead and then first convert all of this number here into its decimal equivalent. And after doing that conversion, divide it repeatedly by 9. And after you do that, you realize that you will still come to the answer 185. So 185 is actually the base 9 form of the number 12212, base 3. So before I proceed, I'll ask, on a scale of 1 to 10, how confused are you? So I'll take it again if you are really confused. If not, we can move on.
5.
I'll say 5. Okay. Is she the only one who stands there? Okay. Okay. So with everyone in the session, what I want you to do is this. If there's anyone amongst you who believes that the explanation I gave is just not satisfactory, but there is a way you can put it that might make Antivider understand it better, please, I'll allow you to step in and then take the explanation for that. If not, I'll just go over it one last time. We have about 10 minutes left. So I want us to at least do question 10.
Then let's
No, question 10
continue.
is
Let's continue.
working. All right. So don't worry, when we are done with the main session, and maybe we can take some extra 5 minutes for you when those who want to leave have left. So this one says that to convert these binary numbers to their decimal equivalents, and that's one of the simplest things to do. I believe we don't have to waste much time on this, right? Let's just take the numbers and do the conversion for one or two of them. So let's do it for this guy and then this guy so that we are fast. So for 0, let's ignore all the extra zeros, and then we are left with the zeros here. Remember, they are not significant. So 1, 1, 0, 0. So this is 2 to the power 0, 2 to the power 1, 2 to the power 2, and 2 to the power 3. And the equivalent to this is 8. And then this right here is 4. So then this brings us to 12. Like that. And then for this guy on the other hand, we have 1, 1, 1, 1, 0, 0. So this 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, 2 to the power 4, 2 to the power 5. So starting from the most significant bit, this is 32, this is 16, this is 8, and this is 4. And the zeros are not significant, so you can do away with them. So 32 plus 16 gives us 48, and 48 plus 8 is 56, and 56 plus 4 gives us 60. So boom, boom. And these ones are quite safe because you can use your calculator to go ahead and punch them. So please, do we agree? It's 60. Come again. Oh, and Brian, don't worry, come again.
Like I was using my calculator, but I had some. I said the one was playing since yeah.
Oh, okay. So there are 4 1s and 2 zeros.
Yeah.
Yes. So please use the conversion. It's 16. Okay. Thank you. So it's 16. All right. Let's look at this side here. And then with this one, you see the numbers have fractional parts. So let's look at those ones. It's just like what we did earlier. It says this one says we are doing 11100.011. We're converting it into its decimal equivalent. So it's the same thing we saw earlier. Let's just go ahead and do it. So we know that this guy here is 2 to the power 2. Oh, sorry. Let's write the number longer so that 111.011. So this is going to be 2 to the power 0, 2 to the power 1, this 2 to the power 2, 2 to the power 3, and 2 to the power 4. This is going to be 2 to the power negative 1, 2 to the power negative 2, and 2 to the power negative 3. So starting from this side, or here, 2 to the power 4 is 16, and then this is 8, and this is 4. These zeros are not significant, so do away with them. This though is significant, so let's see that. 1 over negative 2 1 over 2 to the power negative 2, that's, sorry. This is going to be 1 over 2, like that. And then that's half, which is equivalent to what? 0.5, if I'm not mistaken. So 0.5. And this next one is also going to be 1 over, so 8, like this. 1 over 8 because it's 1 times 2 to the power negative 3, which is 1 times 1 to the power negative 8, 1 divided by 8, basically. So yes, 1 divided by 8 gives us what? On the calculator, is that 0.125, if I'm not mistaken. Can you help me punch that on the calculator? 1 divided by 8 and see?
Mr. Williams, please, did a calculator work? That says that.
Oh, yeah. I believe the installation might be complete by now. Finish. Yeah. So let me find it on my PC and then.
1 divided by 8 is 0.125.
1? 0.1.
1 divided by 0.125.
Yeah, 0.125. Excellent.
Yeah,
Okay.
so that is it.
So 0.125. That's it here. Okay, very good. So then final answer is what we get when we combine our 16, our 8, our 4, our 0.5, and that. So that will give us what? Let me see. That's 16 plus 4 is 20. So 28.
28
plus 625. So that would be what? 28 plus 625, 0.625, right?
Yes, please.
Take the second option, please.
Aish.
No. Go back. Take the second option. Yeah.
All right. Oh yeah, this is very cool. Charlie, there's a free one, powerful. I like what I'm seeing. Okay. So yes, this is what I was saying. So if you want to, please, Mr. Freeman, does it work exactly like your average Casio calculator?
Yes, please, it does.
Oh, okay. So if we wanted to convert this number right here, that's what number did we do? Was it question 1? Was it question 1 we just tackled? Yes, I believe it was question 1. If you want to convert,
it was question 1.
Yeah, so if you want to convert that number, we just come to mode, we select option 4, and then we choose the number system that we are doing the entry in. In this case, it's binary. And we enter the binary number 11100.011. So 111 00.0. Oh, sorry. 11100. It's not accepting.
For
The
binary
point doesn't work.
point don't.
Oh, okay, it doesn't work.
work.
Oh, okay.
So you have to work your way around both of them. But
I
you can
see,
work
I
with the
see.
decimal, the whole number parts, the decimal part.
Oh, okay. And you
Yeah, so
figure
you
it
do
out.
the
Okay.
28 first, then you come and do the.
Oh, okay. That's very smart. Oh, okay. That's very smart. So it's equal to, and then since we have it in binary, we want it in decimal. So you just select this and then you get your 28. So once you get your 28 for this side, the rest of it you will have to, as they said, manually work on hand. So you see, I never really save. Maybe calculators to come will give us the option. All right.
But you can go to the normal mode and then raise to the power like normal raise to the power.
Oh, that's right. That's right. You can use that too. Okay, I see. That's actually smart. So look at this one too. It says we have to convert the following decimal numbers to their binary equivalent. So maybe this is the only one that will make a use of what do we call it? A slight change. So let's tackle this one right here first. So we have 34.75. And we have to convert it into its binary equivalent. So we already know how the whole number part goes. You divide it repeatedly by 2 and you keep keeping your decimal, blah, blah, blah. But I like to convert 34.75 into its binary equivalent. So let's see. We start by converting this side into binary. And I was saying that I like to look at it as break it into powers of 2. 34 is the same as 32 plus 2, right? And then 32 on its own is 2 to the power 5. And then 2 is 2 to the power 1. So for every single one that appears, every power that appears, I assign a 1 to it. And for the ones that do not appear, I give them zeros. So 2 to the power 5 is there, but there is no power 4. There's no power 3. There's no power 2. There's no power, but there's a power 1. Good. And there's also no power 0. So 34 becomes this. The decimal part, on the other hand, if you want to do the conversion for that, what you're going to do is you multiply repeatedly by 2. You keep the whole number, and then you discard, you take the decimal and you multiply again, keep the whole number. You keep doing it till all your decimal is exhausted. What does this mean? I take my 0.75, and since we are doing it into binary, I'm going to keep multiplying it by 2. So I have 0.75. So please, with your calculators, work this for me. So times 2. That gives us 1.50, right? This will give us 1.50, like this. What we are going to do is we're going to take the whole part here, and then we keep that. You keep the whole part. And then you take the remaining decimal part, that's the 0.5 in this case, multiplies by 2 again, so times 2. And that gives us 1.0. So we keep the whole part again, that's 1. Then the decimal part, on the other hand, if it were another number, we would have kept the multiplication going. But since we have arrived at a 0, 0 times 2 will just give us a 0. So that 0 here is insignificant. So our answer becomes 100,010.11. That will be the binary equivalence of the number 34.75. Does that make any sense, or is there any confusion that we need to clarify? I think our time is fast spent now. Okay, it's not fast spent. We are 2 minutes behind, but still. Yeah, so I was asking, is that clear, or are there any confusions that need to be? Let me see if any hands are up. Okay, all right. So I'd like to assume that's clear. All right. So then we can bring the curtain down on today's session. Let's see if there are any ones that you can take and then go and tackle on your own and put the answers on the platform. All right. So this one says convert the following hex numbers to their decimal equivalent, but I see that will not be a challenge. This one says express the following octal numbers in hex notation. So you can change them into decimal and then change from decimal back to hex. That's a good one. Or better still, okay, yes, that's good. This one says you convert the following to their decimal equivalent. This is also a simple one. I believe we can do that, right? And this is interesting. It says convert the following to their decimal equivalents. So you can tackle this one. So 10.12. And this one says convert the following binary to their hex equivalents. Okay, we just looked at that. You can tackle this one too. So remember, groups of 4, and then you convert. You can try this too. So 10.15, 10.16, and 10.12. So we are done for today's session. As always, thank you very much for being a good class, and then I'll see you in the next one. Okay, have a great night. And then let's study. The main campus has begun their exam writing, so ours is just around the corner. Last minute learners association, no, Charlie. In this term, the 1 year while that you'll be overwhelmed. So I suggest you start now. Have a great night, everyone. So, Vida, concerning your confusion, what was it about again? And then let me see if we can go on that before. Vida. Okay. Yeah.
Yeah, hello.
Yeah. Wait, wait, I'm coming. Please, I'm coming. Mr. Joshua, are you the one speaking? Waiting the talk.
Okay, the question is the stolen inside or is your own class?
No, he did the stallings inside. So check chapter 10. Let's be chapter 10. Vida, your question.
Yeah, so what was it about? I think you should go back again. Or it was here that I was confused. Yeah.
I think it's here, this side. Yes.
No, it was this side. It was number 10.
Okay. Okay, so let me just do it quickly so you understand what I was saying. You see, I was
Sure.
implying that we looked at the relationship that's number bases, and then their power bases, the relationship they share. And we said that for any number base, whose, for example, base 8 and then base 2, they share a relationship where base 2 to the power 3 gives us base 8. This means for every base 2 number, like this, if I want to write it in base 8, I just have to group these things into this three right here. Because you said the relationship they shared, if it is b to the power n, to convert from the base b into the other base, all you have to do is group it into the n number of digits. And in this case, that n is 3. So I just have to start from this side, make groups of 3, and convert each of them individually into their corresponding base in base 10. So when I'm doing that conversion for this guy right here, 101, if I convert that, I'm just going to have 5 in base 10. Yeah. And if I convert this 101, let me see, was the number 10? Yes, that's it.
Converting it into binary or decimal.
We are changing this into base 8 actually.
Okay.
The idea is, yes, I'm using the relationship that base 2 shares with base 8. The relationship is that base 2 to the power 3 gives me base 8. So if I'm supposed to convert the base 2 number into base 8, all I have to do is group all its bits into groups of 3. What that does is automatically it forces every single group to be within base 3. Like the idea is when you do that, the maximum size or the maximum digit that you can acquire within 3 bits is always going to be exactly less than 8. You see, the largest 3 bits number is 7. That's 1, 1, 1. And 7 is the largest number inside the base 8 system, right? 0 to 7. Is that all right? Exactly.
Yes.
So when you do groups into groups of 3, you have forced the number system you have forced the restriction on the numbers or the size of the numbers that you can have. So this means this side here is automatically in base 8 because it is from 0 all the way to 7. So it's automatically in base 8. This side here is also in base 8. So then if I convert this one into its decimal equivalent, I would have automatically converted it actually into its octal equivalent, since I am technically working in base 8.
All right,
You
sure. So
see
you
that?
convert all into base 8, right?
Yes. So I'll convert it into base.
If
I'll
you
do it with
convert
the idea of
8 bits,
yes. So 101 is equivalent to in base 10 is 5. But then
yes.
this side is also equivalent to 5. That's automatically
Mm-hmm.
base 8. So this is 5, 5 base 8 automatically. It's automatically base
Sure.
8 because the largest value here is actually 7. So we are working from 0 to 7. That's basically base 8. So 5, 5 base 8. So you apply this even in base 16. If I have 1, 1, 1, 0, 1, 1, 1, 1. And I want to convert that into base 16 from base 2. We know that the relationship they share is 2 to the power 4. So all you have to do is do the same thing, but this time make groups of 4. In those groups of 4,
Okay.
what you are doing is you have forced them to be in base 16 because with 4 bits, the largest number you can represent is 15. That's 1111. And then 0
Yeah.
to 15 is exactly what the hexadecimal system is about. So what this means is currently I have this side here is in 16, this is in 16 too. So I just have to change both of them into their what do we call it? Decimal equivalents. And that's all because of the fact that I'm working within 0 and 15, I am also automatically doing it in hexadecimal. So this will be 15, which in hex is represented with an F, and this will be
Mm-hmm.
14, right?
14.
This will be 14, which is represented with an E, like this. So
VE.
then
Okay.
EF, exactly. So we are grouping
EF
into,
15.
so EF is no,
EF
EF
is
is,
15.
yes, please, is 16, good. So this means that we are just grouping it into the N bits in the relationship. So the N number of groups in the relationship is what you use. Now for this question right here, the relationship that base 3 shares with base 9, it will not always apply, by the way. Like in the case of 6 and then 7, they do not share that type of integer relationship because there is no whole number integer that you will raise 6 to that can give you 7. So you can't apply it there. But for this guy right here, 3 squared is 9. So they also actually share that relationship, don't they? They do, right?
Yes, they do.
They do. So it means we can use that same idea if we take the number 1, 2, 2, 1, 2. That's 1. So let me clear some of this. If we take the number, we take the number 1, 2, 2, 1, 2. We can actually, since the thing here is 3 to the power 2, the n that we group them into is 2. So I form groups of 2 like this to force them to be in base 9, basically like this. And when I do that, you see this guy is a standalone, so you can increase it with a
Yes,
0 so
add
that it
0.
also becomes exactly. And now we can convert each and every single one there into its base 9 equivalent. Doing that forces the number into its decimal equivalent. Doing that forces us to get a base 9 number since we grouped them according to the relationship that base 3 shares with base 9. So the decimal equivalent of this right here, we change it by doing what? It's base 3, by the way. So this is to the power 0.
By multiplying through.
Yeah. And this is the power 1. So this is going to be 2 times 3 to the power 0, right?
Mm-hmm.
Yes. And that's the same as
Yes.
2 times 1. And that gives us
1
2.
times.
Do you understand that?
Yes, I do.
Yes, please. And this is 1 times 2 to the power 1. And 1 times 2 to the
Yes.
power 1 is the same as 1 times 2, and that gives us
1
2.
times
So
2.
this right here
Give you
gives us
4.
exactly. And we come to this side. This is 2 times 2 to the power
Which will give you
0, which is the same as 2 times
plus
1. Hey,
4.
sorry, 2 times 3. We are making a mistake. Sorry. We are working in base 3. Sorry. So this is
Base
2
3, right?
times,
Okay, so 2
yes.
times 3.
So 2 times
6.
3 to the power 0. That will still give us 2. But this one is going to be 1 times 3 to the power 1, and that gives us 3, right?
3. Yes, so making
And
5.
our 3 plus 2 gives us 5. Excellent. On this side, we have 2 times 3 raised to the power 0, which is
3,
the same as 2.
2.
Yes, that's 2 times 3 raised to the power 0. That's 2 times 1, which is 2. And this one gives us 2 times 3 raised to the power 1. That's 2 times 3. That gives us 6. And 6 plus
6.
2 gives us 8
8.
for this side. So this is 8 here. We had a 5 here, but we cleared it. So this is 5, good. And finally, this is 1 times 3 raised to the power 0, which is the same as 1 times 1, which is 1. So the answer we get here is 185, and it's automatically in base 9. And I said, this answer, if you wanted to do it straightforward, this is what you will have to deal with. So you would have had to do your 1. Let me clear all this. So if you wanted to deal with it straightforward, you will just have to assign them their places. That's 0, 1, 2, 3, and 4. After doing that, you have 2 times 3 raised to the power 0, which is the same as 2. 1 times 3 raised to the power 1, which will be the same as 3. 2 times 3 raised to the power 2, which is 2 times 9, that will give you 18. And then you will have 2 times 3 raised to the power 3, which is 2 times 27. That will give you 54. And you also have 1 times 3 raised to the power 4, which gives you, let me see, 3 to the power 4, let me see, 27 times 3, is that 51, right?
Yes, 51.
Yes, 51. So then, no, how, that doesn't sound right. Then it means there's a problem here.
So
Okay,
this
yes,
makes
this was
it
2 times.
2,
Yes, please.
2
That was 2
times.
times. Yes, please. Thank you. So 51. So finally, you can combine all these right here. And then the answer they give you, you will now have to convert that answer into its hexadecimal, into its base 9 equivalent. So currently, if we add all these, we have 51 plus 54, that's 105, 128.
Yeah,
And then after,
128.
okay. And after doing that, we now convert that answer into its base 9 equivalent. So that means this will give us a direct base 10 answer. And then we now divide repeatedly by 9. We take the remainders, and then we finally get a base 9. So you see, that's a little longer than when we do the grouping and then go ahead and then we convert it directly. You understand?
Yes, I'm getting it.
So it's faster to use the grouping when you see the shared relationship. It happens in places like base 2 to base 4, because they also share a relationship 2 to the power 2, base 3 to base 9. They also share such a relationship.
A minute. A
Yes.
minute.
Yeah.
All right, so I'm back.
All
Thank
right.
you.
Right. Yeah. So that's basically it. Okay. That's basically it.
Okay.
Yeah.
I'll take my
All right.
time and go through it one by one tonight
Okay. All right.
and see how
Okay.
best I can.
All right,
But
Charlie.
thank you so
So,
much.
all right. Yeah. So catch you later.
All right, sure. Bye-bye.
Mr. Joshua, good evening.